Hi there, welcome to the Ultimate Physics channel. The topic of today's video is relativistic momentum. What is relativistic momentum and how it is different from the classical Newtonian momentum that we are all familiar with? I'm going to discuss that in this video, and I'm also going to derive the expression for relativistic momentum. So now let's proceed to do that. We all know that in classical mechanics, the expression for momentum denoted by P is equal to mass m of the object times the velocity with which it is moving. So P is equal to mv. If there is a system of particles, then the total momentum of the system, let's again call that as P, is equal to P1 plus P2 plus P3 plus P4 and so on and so forth, where this can be further written as M1 V1, M2 V2 plus M3 V3 plus M4 V4 and so on and so forth. Right? So one can add the momentum of individual entities of the system to get the total momentum of the system. Now, we also know a very important conservation law concerning the momentum of the particle or momentum of a system, and that is law of conservation of momentum, or law of conservation of, to be precise, linear momentum. Right? So this linear momentum in a system involving more than one particle is conserved if no external forces act on the system. So the law of conservation of linear momentum tells us that the total momentum before an event such as the collision is equal to the total momentum after collision, provided no external forces act on the system. So in the absence of any external forces, the momentum of the system is conserved. This is the law of conservation of linear momentum. So we can expect the law of conservation of linear momentum to hold even for systems where the objects travel at very high velocities, that is in relativistic cases. So let us proceed to verify whether this expression holds good for momentum in relativity according to the law of conservation of linear momentum. We know that we can use a collision problem to study momentum. So here we are having two different frames of reference, S and S prime. The origins of these two frames of reference are O and O prime respectively, and we have two coordinates x, y and x prime, y prime. Now we have two objects A and B separated by distance y, and the object A just before the collision event is at rest with respect to the frame of reference S, and object B is at rest with respect to the frame of reference S prime. Right? Now the collision occurs, and each object comes closer for collision to occur. So they travel half this distance, and midway between the two, let us say the collision occurs. Therefore, for the event of collision, the total distance traveled by each object is y by 2 on one side and y by 2 in return. So the total distance traveled by each object in this collision process is capital Y. If velocities of these two objects are, let us say, VA and VB in S, VA prime and VB prime in S prime, then we can write an expression for velocity VA, for example, as the velocity is the distance traveled by the time taken. Let us call that time as T naught. Similarly, this time T naught must be equal to the time it takes for B in S prime also. So this must also be equal to VB prime, right? Because initially A and B were in rest in their own frames of references S and S prime, right? Now what about the velocity VB, that is the velocity of the object B as measured in S? Obviously that is not going to be T naught, because B is moving initially with respect to S. So it's in relative motion, and we know that therefore that time must be a dilated time. Therefore we can write an expression for VB, that is the velocity of object B in S, as VB is equal to Y by T, where T is equal to the time dilation expression 1 minus V squared over C squared. Please do check out our video on time dilation in special relativity to know how we write this expression. And therefore VB is equal to Y by T naught, then denominator is square root of this, so that goes to the numerator as 1 minus V squared over C squared. So this is the expression for VB. So we can say that VB is equal to Y by T naught, we know is equal to VA, and therefore that is VA times the square root of 1 minus V squared over C squared. Or we can equivalently write that as VB is equal to VB prime square root of 1 minus V squared over C squared. So this expression tells us that the velocity of an object as measured in a frame of reference which is in relative motion is equal to the velocity of that object in a frame of reference in which it is at rest multiplied by this factor square root of 1 minus V squared over C squared, right? So if let us say the masses of these two objects in their own frames of reference and in which both the objects are at rest, so respectively let us say the masses are MA and MB for A and B, then we can write an expression P is equal to, that is the momentum of the object, let us call that A, PA is equal to MA times VA. This is the momentum in the frame of reference S, and the momentum of the object B in the same frame of reference S is equal to MB times VB, which is equal to VB prime square root of 1 minus V squared over C squared. And this tells us that when objects travel at very high velocities, which is what relativistic mechanics deals with, we understand that the momentum is no longer simply m times v. Now we know that there is an additional factor that is involved here, and therefore simply we say that if the two masses are equal in the system, and then we can say that if the two masses MA and MB are equal, then momentum is not getting conserved. Simply the momentum is not conserved, right? So here this diagram schematically represents the collision event as seen from S and as seen from S prime. So here we can see that in the frame of reference S, A is thrown vertically upwards towards P, so its trajectory is kind of a parabolic trajectory but vertically, whereas B is in relative motion with respect to S, therefore its trajectory is, because this is moving with the velocity v, its trajectory is somewhat a broader parabola. Now the case for the S prime is reverse. In that frame, the B's trajectory is going to be a vertical projection, so it is a narrow parabola, whereas for A it is a broader one. So this is the schematic representation of the collision event as seen from the frames of reference S and S prime. Suppose the velocities of these two objects, that is VA and VB, the velocities are very small compared to the velocity of the relative motion between the two frames of reference, that is small v. So under that condition, that VA and VB prime, let us say, are much small compared to V. Under that condition, the collision is a glancing collision. That means the two objects no longer have a dominant velocity in comparison to V, therefore their trajectories are going to be governed by the motion of the frames of reference itself, which is the relative motion at a velocity V, and therefore the collision now is going to be a glancing collision where the two objects just barely touch each other, collide and then go away. That is what we mean by glancing collision. So we have these two expressions for momentum of A and B in the frame of reference S, which is MAVA for A and MBVB square root of 1 minus V squared over C squared for object B. Now if these two are the momentum values that we are getting, that means if MA is equal to MB, then PA is not equal to PB. That means the momentum of the two objects after collision is not the same as the momentum of the object before collision. That is, the law of conservation of momentum is violated. So if MA is equal to MB, then momentum is not conserved. On the other hand, if VB is equal to VA over square root of 1 minus V squared over C squared, that is, if you substitute this expression in the place of VB, then we know that these two will cancel, then the momentum will be conserved. Right. So this is the condition under which momentum will be conserved in special relativity, and therefore we can say that if the velocity VA tends to 0 and the mass MA, let us say, of the object is equal to M in S, then this means the mass MB tends to MV, which is equal to M square root of 1 minus V squared over C squared, because this is the mass of object B in S. So this is the mass of object A in S, and this is mass of object B in S, and therefore that would be equal to MV is equal to M over this, and therefore multiplying both sides with the velocity of the motion of the frame of reference, that is relative motion, we can say that left side we have P of V and right side it would be MV over square root of 1 minus V squared over C squared, or simply the relativistic momentum is gamma times MV. This is the expression for relativistic momentum in a simplified way. And this is the general expression for relativistic momentum, and therefore the classical momentum P is equal to MV is no longer valid, and we have a relativistic expression for momentum. And this expression should reduce to the classical expression value under the condition that V is much less than C. That is the classical limit of this relativistic expression for momentum, right? So this is the expression P is equal to gamma mv for relativistic momentum, and as we have already seen, when V is much less than C, that is the speed of light, the relativistic momentum P is equal to gamma times mv reduces to P is equal to mv, which is called the so-called classical limit. Now if you draw a graph between the velocity and momentum, and if you plot, then you would get a straight line for the classical momentum, because P is a linear function of the velocity V, whereas in the relativistic case it is not a linear function, so you would get a curve of this particular type. And for lower values of V, one can see that these two have identical values, the momentum. For lower values of V, as V increases further, there is a deviation and classical values go straight, whereas this relativistic momentum shoots up. Now this particular expression for momentum has interesting consequences for Newton's second law or Newton's force law, that is F is equal to mass times acceleration. Let us proceed to discuss how it is so. Let us proceed to discuss how P being equal to gamma times mv affects the Newton's second law. That is, if P is equal to mv, Newton's second law is force is equal to simply mass times acceleration, because force is a rate of change of momentum, that is gp by dt, which is equal to d over dt of m times v, which is momentum expression. Therefore that would result in mass times acceleration. When P is equal to gamma times mv, on the other hand, force expression will accordingly change. That we call as the correction to Newton's law. How it is so, we will try to derive that. Now therefore it is equal to dp by dt, which is d over dt of gamma times mv, right? And this is equal to, gamma is a function of v, so we have m as the constant outside, then d over dt of gamma v, which is equal to m into d over dt of v over square root of 1 minus v squared over c squared, right? And here if you do the UV rule of differentiation, differentiation of u times v is equal to u dv plus v du. This is the general rule which we are going to apply here. So we take the term u to be equal to 1 over 1 minus v squared over c squared, and our v will be v only. So if you do the differentiation here, u is 1 over square root of 1 minus v squared over c squared, and dv is of course dv plus, of course dv means we are doing as a function of time, so we can simply write dt plus the next term is v, which is v, and you have du, which is differentiation of this whole thing, and that would be minus 1 by 2 1 minus v squared over c squared whole power minus 3 by 2, and then differentiation of this thing is 2v over c squared, right? This is the differentiation, and then of course dv by dt is common here, right? Because the differentiation of that would be there, right? Now we have this 2 and that 2 can cancel each other, and then then there is a minus sign that we missed here, so that minus sign also would be present here, right? That would cancel with this minus, and therefore we would have 1 over 1 minus v squared over c squared, plus the next term is v times v is v squared over c squared, and this you have 1 minus v squared over c squared power 3 by 2. Now it comes to the denominator, the whole thing multiplied by acceleration dv by dt, and already there is a mass there outside, so we have that retained here, and therefore our expression now is equal to mass times the acceleration, and then if I take the LCM, power 3 by 2, so I have 1 minus v squared over c squared plus v squared over c squared, right? So we have 1 minus v square over c square plus this, so these two terms will cancel, so effectively we have ma over 1 minus v squared over c squared power 3 by 2, which is gamma cube ma. So our force equation now is, so this is the correction that happens to Newton's second law. So that is a correction to Newton's law because of momentum being not equal to mv but rather equal to gamma times mv. Thus in this video I have explained the concept of relativistic momentum and derived the expression for relativistic momentum, and I have shown how it affects the Newton's second law, and therefore the need for incorporating a correction to Newton's second law. Thank you.